as you saw, was very narrow, almost a delta function, with these very broad, orders of magnitude lower wings in the Lorentzian that gives rise to the damped Lyman-alpha systems, which I'll come back to in a few lectures. But it must be, you may not be surprised, that the line cores are, that there's additional astrophysics playing a role in the line cores, and indeed it's Doppler motions. So you should picture, well, I guess, a gas like you have around you. That gas has a temperature and motions associated with that temperature. And those gas particles, therefore, have individual velocities, and the Doppler effect gives rise to small shifts in the frequencies, which is given here by equation 42, to first order in V on C. And so if we just keep it very simple for the moment and characterize the gas motions purely by temperature, then we have a Maxwellian distribution for those velocities, which you've seen in statistical mechanics, I'm sure. And then that gives rise directly to a line profile for Doppler broadening, which has the form of a Gaussian, essentially. And a characteristic width in frequency space here, given by equation 485. So that is, in a nutshell, the Doppler line profile. You can generalize it from a very simple gas with a single temperature to one that has turbulent motions, just by recasting this frequency width in terms of both a temperature term and a macroscopic turbulent term. Otherwise, still the same expression as above. More intuitively, I think it's useful to convert from frequency space to velocity space and introduce the so-called Doppler parameter, the B value, a fundamental measure of the absorption line. And so B now is in velocity, kilometers per second, if you will. And you can then, with a Jacobian transformation, convert our frequency line profile into a velocity line profile. And it just got this simple form, again, an exponential looking, Gaussian looking line profile. So to visualize that to the notebook here, I've just cast in that Gaussian profile, adopting a Doppler parameter of 30 kilometers per second, which is characteristic of the Lyman-alpha forest, and you get a line profile that looks like that. Nothing too exciting. But it is, of course, a very steep exponential on both sides, so as we scan down, right, we're seeing nothing like the Lorentzian wings of the natural broadening. Now we're 30 orders of magnitude lower than the line center. There's no these Doppler motions play no role out here in the wings of the line. And it's useful to compare the two. Here's now a comparison of the Doppler profile with the Lorentzian. You can see the Doppler really dominates in the inner regions of the line profile, and the Lorentzian wings carry on beyond that. So the two effects work together. And really, it's the convolution of the two that gives us our final profile, which is referred to as the Voigt profile, just a convolution of this Lorentzian term and our Doppler term. It's a messy-looking beast when you take the convolution. And it's not analytic. But we recognize this, or you may recognize this, I recognize this, as the Voigt profile. Defined here, where A is a ratio of the gamma value that we introduced last time over that velocity or frequency width here in the Doppler term, and U is just the how many frequency steps you've gone off of line center. Okay. And not surprisingly, going back to the plots, you see the convolution of those two profiles. And here you are. So the red dashed line, shows the Voigt profile, which traces out the Lorentzian on large offsets from the line center, and a Doppler term here at the line center. Any questions on that? Okay. So we now have a line profile in hand. I won't dwell on it at the moment, but it's worth pointing out that this Voigt profile is just an approximation. I did mention it was not analytic. I've got some bits in the notes here on how you might go about calculating it. There's actually a pretty fast function in Python, which is actually very accurate. But it's important to note that the Voigt profile itself, despite the fact that it's what we've used, or I've used for decades, it's not a full. It's an approximation to the actual line profile. There are corrections to this void profile, which would need to be taken into account if you want to go to very high precision measurements. Basically, you have to go to second order time-dependent perturbation theory to get the profile correct. This gentleman here is an expert in that, so if you wish to find out more about that topic, pester him. But you can also see this very nice paper by his former advisor, Lee, in 2003. And the bottom line is that despite the void profile, which is symmetric about line center, the actual profile is asymmetric about line center. And you can, in principle, detect that even in the strongest of damped Lyman-alpha systems. But I'll come back to that later. Here's just the description now. This is the term that we've now worked out, basically from the Lorentzian for the line profile away from line center. This is the first order correction term to that, which is obviously asymmetric in the frequency offset. Good. Let's move on to other concepts. Optical depth and column density. We define optical depth here in equation 58. It's the integration along some sightline, some path of the opacity that we've defined. It's dimensionless. Opacity, I'll remind you, is absorption per path length. ds is path length. So optical depth is dimensionless. And it's defined such that it's the optical depth from the observer, me, to the light source, the sun, by convention. Recalling our definition of the opacity, which is the product of the number density in the cross-section, then tau is this simple equation here. And we recognize, or we can define, really the second term in that equation as the column density. So the integral of the volume density along that sight line. So the average volume density along a given sight line. You may not be familiar with column density too much. Perhaps if you've worked on emission from galaxies, you've thought about surface density. That's a physical mass per square kiloparsec, say. Column density is analogous, but it's the number density equivalent. That is the number of particles per unit area, usually reported per square centimeter for absorption lines. I put in the notes here an estimation of the column density of air, say in the room, derived from the volume density, the mass density that we know, and it works out that for a meter of length through, let's see, that's about a meter, through the air in this room, you've got about 10 to the 21, particles per square centimeter of oxygen molecules. That's in hydrogen, what we call a damped Lyman-alpha system. Useful quantity is to estimate the optical depth of a absorption feature at line center. So tau 0 here is the optical depth at line center. And again, at line center, the Doppler profile dominates the description of the profile. So you can write it in this manner. Again, more convenient, at least for me, to think in velocity space. So applying the Jacobian, we would cover this relatively simple expression. The optical depth at line center is proportional to the column density, the amount of gas you travel through, not surprising. The wavelength, the oscillator strength, that's the quantum mechanical description of the strength of the cross-section, and inversely proportional to the Doppler parameter. The more the motions, it kind of makes sense, the broader your line profile, the less deep you are at the line center. For hydrogen, Lyman-alpha, that equation may be expressed as this. So something like 7.6 10 to the 13, which is to say you need of order 10 to the 13, 10 to the 14 particles for gas moving at tens of kilometers per second, turbulent motions or thermal motions, to give you an optical depth of order 1. See that again in the notebook. That's corrections to the wings, blah, blah, blah. This is just the optical depth at line center, assuming a Doppler parameter of a B value of 30 kilometers per second. You reach an optical depth of unity around 10 to 13.6, so hydrogen atoms. And here by a few by 10 to the 14, you're talking about optical depths of 5 and beyond, which is to say all the Lyman-alpha photons are highly absorbed at the line center for a gas with those column densities are larger, highly saturated. We can now make an estimate of the opacity of the intergalactic medium under the ansatz that it's completely neutral. This is indeed what Gunn and Peterson did 50 years ago. We have it for our cosmology. We have the mass density given by the mean density of the universe times the baryonic fraction. We can convert that to a number density, recognizing that of order 30% is in helium. And for a megaparsec, Hubble broadening would dominate the motions of the gas. And those are order a few hundreds of kilometers per second at, say, a redshift of 3. And so we can plug those quantities into our equation now for the central optical depth. You derive a few times 10 to the 19 particles per square centimeter, taking b of order several hundred kilometers per second. You get a central optical depth of about 10 to the 5. This is, again, the classic Gunn-Peterson argument. There's no way one would observe any transmission through the intergalactic medium if it were close to neutral at a redshift of 3. And so the fact that we do see transmission obviously means it's highly ionized. Adopting something that is characteristic of what we estimate the true IGM to be, you get a mean optical depth more of order unity. Any questions on that? So optical depth and column density, they are linearly proportional, more or less equivalent. Although the optical depth also includes the Doppler parameter explicitly in its calculation. Okay, I am not going to speak much about radiative transfer in the context of absorption because it's very simple. Here is a simple expression for for radiative transfer. The change in intensity along a given path is equal to the negative of the opacity times that intensity plus any source term, any emissivity that you have along that path. J is the emissivity. Kappa our usual opacity, and ds is just our path that the photons are traveling along. For absorption line studies with a very bright background source where I initially is quite intense, we can ignore the emissivity, or at least I will ignore the emissivity. There are certainly cases where you shouldn't. And in that case, this equation just reduces to the two terms here on the sides of the next to the equal sign. And that's a very simple equation to integrate. If I divide the opacity on both sides and replace kappa ds with d tau, as I defined it, then we can integrate that. I'm skipping through that just to our simple, very simple radiative transfer equation for absorption. In a nutshell, the incident radiation from the distant source is modulated by e to the minus tau, our optical depth that we just defined in the previous subsection. Okay. Great. So we now have all the pieces in place to make our first absorption lines. We have a line profile. We have atomic data, energy levels, and oscillator strengths, and spontaneous coefficients. We've got a definition of optical depth and column density, so a physical quantity column density that characterizes the gas, and we have a very simple equation for the radiative transfer. Putting all the pieces together, let's make an absorption line. That's the calculation we just did. I'm going to draw on a few tools, again, or classes from this line tools package. These are all in the notebook, so you can play with this yourself. I'm making up a fake spectrum around Lyman-alpha. No instrumental source, no sources of the instrument here, no resolution, no signal noise, just a perfect instrument. And generating void profiles from our absorption line. So I guess the first one I'm going to show has a column density that is of order unity optical depth as we just derived for Lyman-alpha. And voila. There is reset that. Oop. An absorption line, very exciting, for Lyman-alpha. And at this column density, all the profile is dominated by that Doppler line profile. So you're just seeing the Doppler broadening of that central line. It's a little more fun to look at a series of absorption lines. So here we are. I'm just varying, I'm keeping constant that Doppler parameter, but varying the column densities from a very weak line, 10 to the 12 particles per square centimeter, up to this damping regime beyond 10 to the 21 particles per square centimeter. Now you can see the Lorentzian wings manifesting themselves now in flux. These are flux profiles, again from our simple radiative transfer equation. And I'll zoom in on the very central lines. Again, only varying column density here. Oops. We can see a very weak absorption in the 10 to the 12 column density, this 10 to 13.6, which I showed you. And then as we showed, when you go above 10 to the 14 or so in column density, the central optical depth well exceeds unity, and the lines are completely saturated. There's no flux transmitted through the cores of those absorption features. Somewhat similarly, this is the same plot, but now in terms of velocity instead of wavelength. And again, the Doppler parameter here is 30 kilometers per second, so that width is of order 30 kilometers per second. All the broadening here is due to the increase in column density, not to the increase in the Doppler parameter. And you're just seeing further out into the Gaussian as you increase the increase the column density, which increases the optical depth of the line. And vary the B value. Not surprisingly, you just see broader and broader features as you go to higher and higher Doppler values. And trying to vary the B value, or varying the B value for the case of the damping wings, you see no effect. Those are three profiles right on top of each other. All of the broadening is within the core of the line, and you're not sensitive to that whatsoever when you are dominated by the Lorentzian wings. Good. Any questions on absorption lines? Okay. Idealized absorption lines. Let me define equivalent width. It's a gross measure of the flux absorbed by the gas cloud. It's really the convolution optic depth of the line profile. It's a observational quantity, not a particularly physical quantity, although it does derive from the astrophysics of the line. But it's primarily an observational quantity. Conveniently, it is independent of the spectrometer. Okay, so whether you measure an absorption feature with the highest of resolution to shell spectrometers or a very low resolution prism, the equivalent width that you measure is independent of that spectrometer. That's at least useful. You should visualize it really as the area under the curve, or above the curve really, in an absorption feature. So here is a demonstration of that. Put it on the screen. On the left is an actual absorption profile, okay, and the equivalent width now is the area above that curve in this normalized spectrum. And if you like numbers, it's of order a few tenths of an angstrom. And I guess we use the phrase equivalent width because that 0.16 angstroms is the width of a boxcar artificial absorption feature that would have identical equivalent width to what we've measured in a real line profile. Okay. Here's the actual equation for the equivalent width, just integral 1 minus the normalized intensity. Again, from our simple equation for the radiative transfer, we can replace the ratio of the intensities by e to the minus tau, and that's what we recover for the equivalent width. It's defined as positive for absorption, so that means emission is negative, despite the fact that emission people use positive and negative for absorption. I feel like we were there first. I don't know, maybe we weren't. Anyways, if you're speaking in absorption lines, then equivalent width is positive. I suppose if you're speaking in emission lines, then equivalent width is positive. I won't go to the notebook for that. So curve of growth describes the mapping of the optical depth of the line to the equivalent width, as it was just defined. There are three primary limits within that one discusses within this regime. The first is the very weak limit, where the opacity, the optical depth is very small. Tau 0 is much less than 1. In the limit that the optical depth is very small, then we can ignore the Lorentzian, and our optical depth is just given by, again, by the Doppler line profile. And the equation for the equivalent width simplifies very, very much. When tau is small, then E is about, the exponential of negative tau is about 1 minus tau. So the term inside the brackets reduces just to a tau. Okay, and we integrate over the line profile to recover this. So the equivalent width is proportional to the wavelength squared, the oscillator strength, and most importantly, the column density. So in this limit where the optical depth is very small, the equivalent width scales linearly with the column density. That's valuable. That is to say, if you have sensitive enough data to measure small equivalent widths, then you can directly estimate the physical quantity, the column density of that gas. Independent of the Doppler parameter, there's no Doppler broadening in this term. It just depends on a few, just the quantum mechanics, the energy level, and the oscillator strength, and this column density. We refer to this as, therefore, the linear portion. It's both the weak or the linear portion of the curve of growth. Again, equivalent width is proportional to the column density. And here is an expression for our favorite Lyman-alpha line. A column density of maybe roughly 2 times 10 to the 13 gives you an equivalent width of about 1/10 of an angstrom. Here's a visualization of that. Again, just a weak line with an equivalent width of about 0.05 angstroms. Okay. In the strong line limit, where the optical depth is of order unity, a few, maybe 10, 20, we can again ignore the Lorentzians. We're not sensitive to the wings until we're at optical depths of order 10 to the 8, 10 to the 9. And our Doppler profile is just a Gaussian-looking profile. So the optical depth in a dimensionless quantity here is the central optical depth times this Gaussian. What we can consider is how far out into the wings of this Gaussian profile do we have to go until tau is about 1. It's easy to solve for that. You get an x value which goes like, maybe just write it out, tau x, right, line center, e to minus x squared. And then we solve for where tau x equals 1. That just gives you x1 equal to square root of the natural log of our line optical depth. Again, the central optical depth is only really primarily proportional to the column density. So that means that our equivalent width, how far out, how wide that line profile is very insensitive to the column density. Now it's going like the logarithm of the column density and then even the square root of that. Or more explicitly, the equivalent width goes like the logarithm of the column density and the square root of that. So we've lost sensitivity in this limit, in this regime where the optical depth is of order unity or even several times that to the column density. Instead, the equivalent width is dominated by the Doppler parameter, the turbulent motions within the gas. So here is a saturated line, column density of, say, 10 to the 16, and the equivalent width is of order unity as well, 1 angstrom, 0.6 angstroms precisely. To illustrate better, to really illustrate how insensitive we've become to the physical column density of the gas, let me show some line profiles. So here are two line profiles with an order of magnitude difference in the absorption column density, very identical Doppler parameters, and you can see the equivalent widths are only different by about 20%. Okay, so yeah, the line with 10 times the column density is a little bit broader, a little bit stronger, but just barely. And where this really hits home is that if you observe a line, if one were to observe a line profile like that, you really could not distinguish between a gas that had 10 times higher column density, that was what I just shown, or a gas that had the same exact column density amount of material as the original line, but just a slightly higher Doppler parameter. Okay, so in this saturated regime, you're fully sensitive to the motions within the gas, but almost entirely insensitive to how much material is there. All right, so the red and green lines, that's indistinguishable with real data, unless you have just exquisite, even with exquisite solenoids, that is indistinguishable. And so you've lost sensitivity to the amount of material in this regime. I've put into the notes kind of a classical way of describing or estimating that that equivalent width in the saturated regime. But let me jump to the third regime, which is the damping limit. Now we have the central optical depth much greater than unity, and we become sensitive to those Lorentzian wings. Here again is the damp Lyman-alpha profile to compare against what you get for just a saturated Maxwellian profile here at the line at the middle. Now tau x goes not like this Gaussian, but like our Lorentzian. So tau naught like 1 over x squared, essentially. And we can ask how far out into the wings do we have to go until we hit an optical depth of order unity, which would be where the flux would no longer be significantly absorbed. And working through that, you quickly see that distance x goes like the square root of this central optical depth times the a coefficient to the 1/2 power. A is just a quantum mechanical property. It's tau naught again, now to the 1/2. That describes the astrophysics, and tau naught being proportional to column density means that our equivalent width is also proportional to column density. So in this damping regime, we have an equivalent width that is sensitive to the column density, but only as the square root of the column density. So putting that all together, there it is formally. Putting that all together, the weak limit, you should hold in your head an equivalent width of order 1/10 of an angstrom or less. The damping limit is beyond 10 angstroms, and the saturated limit, where you have very little sensitivity to the column density gas, is everything in between. That's 2 orders of magnitude. The in-between is really just 2 orders of magnitude of equivalent width for 6 orders of magnitude of column density. And this is what makes it difficult to characterize gas in a wide range of environments, unless you have access to higher order transitions of the Lyman series. And here it is. Here's the full curve of growth now in terms of one figure. Ranging, this is all for Lyman-alpha. Ranging the column densities from 10 to the 12 out to 10 to the 22, so 10 orders of magnitude in column density. Here's this weak or linear limit, the correlation between equivalent width and column density being linear. The saturated regime, where now you see we travel many orders of magnitude in column density and very little change in the equivalent width. And the damping regime, where now the equivalent width goes like the column densities to the 1/2 power. Any questions on that? Great. Okay. That ends the nitty-gritty astrophysical part of the lecture. Let me transition to some notes on spectroscopy. So some spectral basics. And I'm going to have some slides that go with this too. So just want to provide a few useful definitions on spectroscopy. This is not a course in spectroscopy, although we are using spectroscopy to study this gas both in absorption and emission, so it's nice to have us on the same page. I wanted to point out a few salient aspects of spectroscopy that we use when describing the data. sometimes misuse, so I wanted to put us on the same page, at least on my page. The first thing to note is when it comes to spectrometers is that the line spread function, which is you should view as the shape of a monochromatic source that's put through the spectrometer, that shape, that line spread function depends on the actual instrument that you're using. Mostly, I suspect most of us in this crowd use either slit spectrometers or fiber-fed spectrometers. Those two profiles are shown here. The slit profile is the sync x squared profile, which is in black. The Gaussian profile is what you get from a single mode fiber in blue. They're very similar. Okay, so to 0th order, most of the spectrometers that we play with, you can approximate as a Gaussian, if you prefer, I suppose, the sync x squared. It turns out that imperfections in the spectrometer also push you towards and the central limit theorem also push you towards a Gaussian-looking profile. So by and large, and for the remainder of the school, it's reasonable to assume a Gaussian line spread function, but that need not be the case. So buyer beware. If you're working on a new instrument or a new spectrometer, it's best for you to characterize that line profile yourself, that line spread function yourself. But we'll just assume a Gaussian going forward. Under that assumption, let me define the resolution. That's the characterization of the width of that line spread function, the physical width. It is dependent, again, on the line spread function, but we'll assume the Gaussian. It's dependent on the slit width that you use, or the fiber width that you use. Okay. And if you're using a slit, it's even dependent on the size of your source, right, which may mean the seeing that you're observing with. It's dependent on the dispersing element, and it's not dependent on the detector. Okay? Characteristics of the spectrometer, possibly characteristics in the seeing, not characteristic of the detector. I think a proper definition of resolution, at least in the case of a Gaussian line spread function, is the following. It's just the ratio of the wavelength that you are observing at over the spread of that line, the full half max of that line at that wavelength, lambda over delta lambda. For some numbers, some common spectrometers, the SDSX fiber-fed spectrometer has a resolution, this RF value of around 2,000. Shell spectrometers have tens of thousands. The new Pepsi instrument on LBT, I think, can go up to 300,000. Pretty impressive. The Echelon spectrometers, which have very high throughput, are a little bit more modest in their resolution, something of order 10,000. We can express this maybe for convenience, but also for astrophysical intuition as C over R. It's to divide the speed of light by this R value. And I often refer to my spectrometers in terms of the spectral resolution of that quantity, C over R. For example, an Echelon spectrometer has a resolution of order 10 kilometers per second, okay, in that notion. The old timers in the crowd may still use angstroms. That always makes my head spin, but you also hear resolution in terms of the full half max in angstroms. For completeness, let me introduce a few other quantities. Dispersion now, that's the width of as I define it, and I think is the way it should be used, it's the spectral width of 1 pixel on the image that you've recorded. I suppose it makes maybe a little more sense to be the width of 1 pixel on the native pixel on the detector, but we can often bin pixels on the detector, so it's generally makes a bit more sense to actually speak of the recorded data as opposed to the native pixels. But that you should be thinking of just the width of a pixel in your spectrum. It's therefore highly dependent on the detector, the size of the pixels, and whether or not you've actually binned on the detector. Cautionary note, a lot of people refer to the dispersion as the resolution, but don't. Dispersion has, I wouldn't say nothing to do with the resolution, but they are distinct quantities. Sampling is the number of pixels per resolution element. So that's quite straightforward, that width in lambda over delta lambda. And to resolve an absorption feature or an emission feature, you probably appreciate that you need at least a sampling of 2 pixels to achieve the so-called Nyquist limit. And then lastly, solenoids, ratio of the observed flux to its uncertainty, all right, that you're probably already fully aware of. To hit home or impress upon you further the notions of resolution, I put together this somewhat complex figure. These are three spectra of the same quasar, one of my favorites. Here taken by the Sloan Digital Sky Survey, so R of 2000, here taken by an Echelette spectrometer, R of 8000, and here taken by the HIRA spectrometer and a shell spectrometer at R of about 30,000. It's the same wavelength range, it's the same quasar, it's not the same solenoids, but you can see quite clearly the effects of resolution as we go from the shell, say, down to the Sloan. Here's now here on the right here is a zoom in of just a snippet of the spectrum, 4270 up here. And again, comparing the Sloan in blue to the Echelette to the Echelle spectrum. I think you can see even by eyeball that the Echelette data is actually pretty good at resolving most characteristic features of the Lyman-alpha forest. So an R of 10,000, or that C over R of 30 kilometers per second, is sufficient to capture a lot of the information within the Lyman-alpha forest, but maybe not all. We have 5 minutes? 7 minutes. All right, okay, great. Again, back to the notebook. Here now I'm making up fake spectra given some resolution, some sampling, and as you wish, some signal noise. A idealized Lyman-alpha line again, here with a central optical depth of 1. So here's here's a perfect, that makes the perfect Lyman-alpha line, and now I'm making a spectrometer with an R of 30,000 sampling of 3. And here we are. So the black is the perfect line profile. You can hardly see it. And the blue is an Echelle spectrometer description of that perfect line profile. And you can see at Echelle quality data, you have a nearly perfect description of the line. This is for a Doppler parameter of 30 kilometers per second, so that's very well resolved. Go to an Echelette. I've just changed the resolution and made no other changes. That also is quite a good description of the data. The green now is the Echelette. The black is the perfect profile. But eventually, as we go to an R of 2000, now something characteristic of the Sloan survey, say, right here, barely getting any absorption at all. And that's before adding in, right, the effects of noise or something about to mention continuum uncertainty. So let's add in some noise. Now a Sloan spectrum with signal noise of 10, which is quite good for the Sloan survey. Yeah, I don't know, maybe you get a fluctuation that looks fine. Who knows, maybe not. Okay, continuum. Another aspect of the, this is really now for absorption line studies. To do the experiment, we need a background light source, and to study Lyman-alpha, we need one that's bright in the far ultraviolet. There are some options. I am focusing mainly on quasars because that's been the most productive over the past decades. But gamma ray bursts also emit at far ultraviolet wavelengths. Even a star-forming galaxy has flux at Lyman-alpha, as you all know, and beyond that as well. So there are other sources in play. So we need this background source in order to measure the absorption, but we don't really care about the background source in order to measure the absorption. So we are required really to divide out its effects, its spectral energy distribution, and that's what we refer to as continuum normalization. I'm going to give you I'm going to emphasize the quasars, but this holds true whether or not you're using quasars, gamma ray bursts, or star-forming galaxies. In terms of quasars, you may appreciate there's significant source-to-source diversity in the strengths of the emission lines and the slopes of the just the kind of overall continua. And the absorption features even, there's intrinsic absorption often in quasars. And all of those are unwanted aspects of the analysis that we need to address. Here I'm just showing two otherwise very similar quasars, but with rather very substantially different features going on at the line. Typical line emissions is Lyman-alpha, silicon-4, and carbon-4, and you're seeing strong absorption in one case, some associated absorption, and essentially none in the other case. And one needs to take that into account, characterize that before doing the absorption line analysis. Another challenge, mainly for quasars, especially for quasars, I guess also for galaxies, is that the emission properties of these phenomena are very poorly understood at the higher energies, beyond a Rydberg. We have limited physical intuition. I guess that's true in general, but even more so at these energies. And it's very tough to get an empirical assessment as well. That being said, quasars do hold similarities from case to case. I'm plotting here two composite spectral energy distributions. One from redshift 1 from HST data in black, and the other from redshift 2 in blue from the Sloan survey. And to 0th order, those are quite similar spectra. They're not identical, but they're quite similar. And the similarity actually really becomes very close if you restrict yourselves to the higher redshift samples. And this is actually kind of even hard to see in this figure. So it's a complex figure. It's a set of panels of stacks of quasars, or average quasar spectra, ranging from around 2.2 up to 5, all from the Sloan survey. And in each of the subpanels, there are three of these composite spectra plotted, blue, green, and yellow on the top, or blue, green, red on the bottom. And these are right on top of each other, okay? So this is, again, this here in this panel is ranging from 2.5 to 4.3, hundreds of quasars per spectrum, per composite spectrum. And at the several percent level, the average quasar SEDs are nearly identical. So there is some hope, there's quite hope, in being able to at least model the background continuum and divide it out to perform our absorption line analysis, given the, at least on average, similarity in the cohorts, whereas of course, from sightline to sightline, there can be significant variations. Maybe I should pause there. 2 more minutes? Yeah, okay. I think I'm going to pause there. When I resume, I'll show you just 2 quick techniques on continuum fitting. One which is by hand, which will scare you. But some of the more important, I'd say, discoveries even from absorption line techniques have relied on the human by hand making estimates of that quasar continuum, and some more modern techniques related to PCA analysis. But I think I'll stop there and see if you have any questions on where we made it today. Please.
Yesterday you spoke about the spin-orbit interaction and its addition in energy.
Splitting, shifts in energy of the, well, for spin orbit, just of the 2p state. Mm-hmm.
And that gave a shift, and I was wondering how that relates to the dispersion and to the resolution here. You said there might be a velocity shift. Which
so yeah, in terms of the quantum mechanical corrections to the class, the simple Hamiltonian, that leads to a change in our energy levels for the Lyman-alpha line and the Lyman beta gamma, all the Lyman series. Okay, but we then go forward with those energies as our rest wavelengths, or as our rest energies. And that does not, so anything I've shown you here.
If you don't take that into account and then you do this, what's the difference?
So yeah, the shifts were of order of 3 kilometers per second,
okay. Yeah.
which for these shell spectrometers is about half the resolution element.
Yeah.
So that's a shift of half that line spread function, several pixels,
So
easy to measure,
big difference.
trivial to measure. I'd say you could measure it to a factor of 100 precision with a decent spectrum. Mm-hmm. So absolutely required. Yeah. Anything else? Good. Okay, well then let's break, and you can pester me over coffee as you wish.